So in this section, we'll be concluding our initial discussion on the review of thermodynamics or classical thermodynamics. So in this part, we'll discuss chemical equilibrium. So we'll be particularly considering a reaction, a general reaction of the type, let's say A plus B, or maybe we can actually write the stoichiometry of the reaction in terms of notation as nu A. So A and B are reactants, and let's say C and D are products. And then we ask this question, like at time 0, let's say, what is the amount of any product? Let's say Na is something like Na0, where Na0 corresponds to the amount of Na at time 0. Similarly, Nb corresponds to Nb0 at time 0, and so on. And in this way, if you ask that at any arbitrary time, let's say when time is t, what is the amount of Na? So this will be the initial amount Na0 minus it will have nu A into xi, where xi is the advancement of the reaction. And similarly, Nb will be Nb0 minus nu B into xi, and similarly Nc will be Nc0 plus nu C into xi. The plus sign is here because the Nc, C and D are products. So with respect to time, they actually accumulate, and we'll have Nd0 plus nu D into xi. Now if you ask, if you take the derivative now, or the differential dNa, so that will be, look at it here carefully. So Na0 is a constant, nu A is also constant. So it will be simply minus nu A into d xi. Similarly, dNb, that will be minus nu B into d xi, and similarly dNc, which is the differential change in amount of C, will be plus nu C into d xi, and similarly for dNd, it will be plus nu D into d xi. And then we can actually combine everything and ask this question, what is the change in Gibbs free energy? We know that for an open system, the Gibbs free energy will be minus S dt plus V dP plus the change of the moles of the constituent. Here the constituent I am writing as I, so I is basically A, B, C and D, and we have nu I dNi. Now the way I have written it here, when I write it for A and B, I should write nu I for A, I have to write minus nu I, because I have to include the negative sign in the stoichiometry. So at constant pressure and temperature, it is just the nu I dNi, and we can actually now express it in terms of the d xi. So instead of nu notation here, we can actually write it as mu, the chemical potential, because that was what usually the textbook write. It's for chemical potential, and the nu's we are preserving for the stoichiometry. So the mu I, as we can see here, is nothing but mu I is mu I times d xi, with including the sign, and then we can actually write it as the dNi part, not the mu I. So this should be the dNi part, and then we can just write it as mu I into d xi with the sum. For example, we can simplify it, let's say for a reaction which is going from A to B, and then it's only the constituents are A and B, then we can show that the dG at constant pressure temperature is nothing but we'll have A to B. So for A, if I take the summation, it will be minus mu A plus mu B into dxi. So we can ask this question now, what is this quantity del G del xi? So it's basically the differential change in Gibbs free energy per unit advancement of the reaction at constant pressure and temperature. That is simply, as we can see, is the difference in the chemical potential of A and B, and which actually we define as the reaction Gibbs free energy. So it's a change in Gibbs free energy for a reaction, that's why you write a suffix R here, and that is just difference of the chemical potential of the constituents. So again, any mu, we can actually write it as mu I0 plus RT ln Pi by P0, and then we can actually replace it, and what we see here, we'll have some terms like mu A0 minus mu B0 if we collect the standard state chemical potentials, and then we'll have RT ln Pa by Pa0 divided, it will be B because A has a negative sign, and then I'll have Pa by Pb0. So this is basically the reaction free energy, and then we can further say, so now you can actually define, let me first rewrite it, the reaction Gibbs free energy. The way we got it is something like a combination of mu zeros. If we write it as the standard state chemical potential or standard state of the reaction Gibbs free energy, which is nothing but the differences of the mu I zeros. So basically for reactants it will be negative and for products it will be positive because it is coming directly from the stoichiometry. And then the other part which we will have is basically RT ln Pb by Pa, because the standard state for Pb and Pa are basically same in this case. In every case, of course, but if we have a stoichiometry something like of the reaction, something like say A is going to B, then we should have actually raised there will be a nu I also associated with it. So overall, what we can write for this reaction is if we have this quantity, which we define as the reaction quotient, so we write it as delta R G naught plus RT ln Q, and we also define that when at equilibrium, so there is no forward reaction or backward reaction, so the reaction Gibbs free energy is 0, which gives basically delta Rg is minus RT ln Q at equilibrium, and at equilibrium we replace the Q as equilibrium constant, which is K equilibrium. So we can just rewrite this equation again, that the reaction Gibbs free energy is nothing but minus RT ln K equilibrium plus RT ln Q, where Q is the quotient. So the quotient will be the equilibrium quotient if the system has reached equilibrium. And then we can also do it for a general reaction, in the sense that if we preserve the stoichiometry number, the nu i's also, so then eventually one can show that this quotient will be nothing but the pressure of the, let's say the way we started it, A plus B is going to C plus D with the stoichiometric quotients as nu A, nu B, nu C and nu D. Then in the numerator we will always have the products. We will have P C by P0 to the power nu C, P D by P0 to the power nu d, and then we'll have PA by P0 to the power nu A, and PB by P0 to the power nu B. And then we actually say that a reaction, what will be the effect of external conditions like say pressure, temperature, or say inert gas on the equilibrium constant. That we try to understand, and then if we carry out the maths, we will see that this equilibrium constant, it can be you can have many effect on the effect of say inert gas or say temperature. For that actually we use a principle which is known as the Lassiter principle. Already you know these things, so I am just giving you an overview. And then we talk about the effect of inert gas and talk about the suppressed dissociation or enhanced dissociation depending on the stoichiometry of a reaction. And also we talk about the temperature dependence, which is related to the Van 't Hoff equation. And there we showed, I mean you can actually look at the video for my earlier course, where we showed that this quantity, instead of ln k equilibrium, we can actually write it as d ln k equilibrium after some manipulation. And then you can easily show for any reaction it is basically connected to the change in enthalpy divided by RT square. Now if the reaction is exothermic, so then delta H will be negative. So with respect to increasing temperature, actually you have the reaction rate, the equilibrium constant will be less. And for an endothermic reaction, if I keep on increasing the temperature, I will have basically the equilibrium constant, the value of the equilibrium constant will be increasing. So the equilibrium constant is a function of temperature only. So if we do not change the temperature, the constant will not change. Then what we can say from this is that for endothermic reaction, increasing the temperature will give you more and more ratio of the product. But for exothermic reaction, it is the other way, because heat is released and something is absorbing. So you have a lower temperature, you have a quenching of the heat. But for exothermic reaction, you usually need optimal temperature. The reason is actually you have to break bond to activate the molecules. So one of the very good example is the catalytic reduction of nitrogen to form ammonia, which is extremely important for our survival. It's an industrially important reaction, and which actually is the key reaction to produce many fertilizers. And here this reaction is exothermic, which means heat is produced in this reaction. And then if you reduce the temperature too much, the reaction does not occur, because initially you have to break this nitrogen-nitrogen triple bond to get basically radical form of the nitrogen, which are adsorbed of course on a surface of metal. Usually it is iron catalyst is used, but this triple bond breaking actually needs a lot of energy for activation. So to overcome that energy barrier, you need some initial temperature, otherwise the reaction will not occur, and that's why we talk about the optimal temperature. And moving on, then we actually discussed in the earlier course that what about the electrochemistry or the thermodynamics of electrochemical cells. And there is the same concept, that you start with the concept of the reaction Gibbs free energy, which we just developed, and by definition it is basically the differential change in Gibbs free energy per unit advancement of a reaction. But this reaction is now an electrochemical reaction, and it should be of course at constant pressure and temperature, because we dropped the two terms VdP and SdT. And then we kind of equate that the work done, or the differential work done, I am writing d cross again because the work done is not an state function, or this d cross w is not an exact differential. The electrical work done, if you think that I am moving a positive charge across a potential, then it will be minus nu F, the E cell, which is the electromotive force of the cell, and times the dψ. So we can now think that this dg will be nothing but equal to delta Rg and times dψ. Of course, this is at constant pressure and temperature, and then we can compare these two equations, and then we can actually get an expression for the electromotive force of the cell, and then we will get the differences in the reaction gives free energy, which at the standard state, which for the reactant minus product, divided by nu f. So here f is the Faraday constant and nu is again the number of electrons which are being changed in a redox reaction, which are involved in the redox reaction, divided, and then we have one factor RT by nu f, and we are keeping the same notation nu. Usually in many textbooks actually write it as n, RT ln q, and then one can actually write that at equilibrium again this will be 0. So then I will have minus delta Rg nu f minus RT divided by nu f ln q at equilibrium. So this constant is nothing but something like an equilibrium constant, but we just write it for cell reaction because it is equilibrium constant divided by the nu f. So we use usually that notation, which we write it as E0 cell, which is the standard this chemical or the electromotive force of the cell, electrochemical cell, in the if the everything is in a standard condition, and then minus RT by nu f ln q, where q is the reaction quotient, and this equation we call as Nernst equation. And from the Nernst equation one can actually get the electromotive force of a cell, but when you do a problem you have to always remember that what drives the cell reaction is the free energy. So you have to always take the nu f times E cell to understand the driving force of the of any electrochemical cell, and this equation is known as the Van 't Hoff equation. So in the next few lectures we will be first starting with the advanced topics. So where we will not give you an overview of phase diagram or the multi-component phase diagram here, because that has been already covered in the earlier courses, and it is mostly covered in engineering thermodynamic courses. And second point here is that so from in the next set of lectures we will be covering a few aspects of the intermolecular interactions, where we will first talk about what is the driving force behind formation of the liquid state, and then we will be talking about the self-assembly of macromolecules, and where we will show that how basically what is the fundamental physics behind say coagulation or flocculation of colloids, and what is the stability of colloids, those kind of issues. So we will be talking about the overall electrochemical aspects of this thing, of this macroscopic system, but of course we will also give you some aspect of understanding to some level of understanding of the microscopic picture also. Thank you.